Our next presentation is about a project which has lasted in ESTHub for a while, namely in the climate zone nearby Baltic states. Still we have 4 seasons. Especially we have experienced last winter, and if our earlier presentations were about larger and smaller structures of liquid water, so this presentation is about meltwater or ice. From Tallinn University of Technology, Sander Rikka is presenting to us insights of this ice processing algorithm.
Hello, everyone. I hope I'm here.
Yes, you are.
Thank you. Hello. My talk today is about developing an operational ice segmentation and classification service, which was done during the project ice charting using remote sensing methods. And I couldn't have done this without my colleagues from here in Tallinn University of Technology, as well as in Keskkonnaagentuur. Our initial goals of the project, the acronym YAG was used most often, was to automatically detect ice and classify it according to official ice chart that Keskkonnaagentuur is providing for every day during the winter. It includes 9 different ice classes for the coastal seas. For lakes, there is no mandatory ice charts. Well, we don't have to produce any ice charts. And this was maybe one of the good areas to develop or test the fully operational service from satellite product to the website. And then again, we had to produce ice thickness estimation for lakes, and also start several different workflows on ESTHub for various products. Yeah, the required outcomes are listed here. You see Sentinel-1, 2, 3 visualizations basically that are on the website at the moment. Then the ice products was one big part, or the main part, where there was several smaller aims. First segmentation, then classification. Well, ice edge detection is part of both actually, and then determining the ice sites as well. Thickness, coherence, and then at some point during the project, the snow mask and cloud mask from Idebix algorithm was also added. And then from Copernicus Marine Service database, one product visualization was also included during the project. So a little bit the background of how ice charting is done or was done previously. Basically, all available sources come together on the expert monitor, and then they manually draw lines over the areas or areas which correspond to one ice type. There is a plugin for cookies application which enables it and makes it a bit easier, but nevertheless it requires a lot of manual work, and if somebody wanted to do this really accurately, it takes a lot of time. So our project goal was to again do this partly automatically, that highlight the areas, for example, here, and reclassify it as one type of ice. Even though the ice charts are available since 2014, that I have access at the moment, the digital files basically started one season before our project. So that limited our available data for matchups with SAR. So only 23 images and 27 images for interferometric and extra wide swath correspondingly, which is not much. And our making the annotation for machine learning application, we first segmented the whole image, these green squares and different various areas highlighted here. This is done by an already existing algorithm. Then we opened this R image, the green segments, then the official ice charts on cookies, and we manually added together or labeled the green shapes with corresponding ice number. And you see that in this case, actually, we had to do quite a bit of error control, maybe. For example, here in this area where the official ice chart says it's some kind of ice, I don't know at the moment which type, but it actually includes water here. So we had to critically look over all the values that are assigned for each official ice chart and label it accordingly. And next step would be to calculate a bunch of statistics for each area here. Examples are basic averages, standard deviations, polarization ratios, percentiles, and texture parameters using gray level coherence matrix methods. Also, we included the incidence angle mean, which is the most relevant. In total, about 300 parameters, which seems quite a lot, but actually using gray level coherence matrix methods, you can produce double the size of these parameters easily. It's not a big problem. And finally, in previous step, we made the annotation image, this blue segment here added together. This was then, or this information was also included in the large database. And the goal or the hope was that using this statistics here over this area, with machine learning, it would say that, oh, this is number 7. It means open water. or other areas with similar fashion. And now that we have all the data, all the statistics, which are now called features in machine learning world. We somehow had to make a selection from them. It's not very efficient to calculate hundreds of values for each area and then give it to the machine learning algorithm or model and try and figure out something. There is a method, at least one of them is Fisher score, that gives estimation on how well each, let's say, average value here, for example, average value here corresponds to the ice class number. Not in all cases, the Fisher scores gave meaningful results, in a sense that, for example, being in a radar or SAR field for many years, I would say that incidence angle is a relevant information, whether it is or is not related to the ice class. So this expert here is basically us, and we think that, oh, you must know this information to produce relevant results later. And depending on the application or the area, basically 20 to 30 parameters is all that is needed for the machine learning to produce some results. And here I must say that all the 9 different ice types, or estimating them using our data set was not at this point, or maybe still is not possible. And that's why we agreed to have only water and ice classification first, and then the ice areas are divided into 3 different types of ice: fast ice, strong ice, and weak ice. Here is the data amount for different applications. You see quite large inequalities between water areas or water segments and ice segments for sea areas at least. And if it used all of this information as it is in model training, we will get strong bias for the water area. And that's why we had to reduce the water samples and make them more equal to ice areas. And then you see little asterisks here. So I'm not entirely sure that these are exactly the numbers that were used in the model training. Going through all the old code and files was a challenge. But I believe they are in the same area, at least in 10,000s for water and ice. And here, I believe they are relatively correct. For lakes, we had a lot bigger data set. They are much more equal. So I believe those numbers were actually the data amount that were used in model training. For ice thickness, the story is quite the opposite. Most of the measurements that were available for this thickness estimation model was collected during the 2018 and 2019 season. 2020-2021 winter was quite mild, if I remember correctly, and there weren't many ice thickness data collection. All in all, we basically have around 50 to 60 measurements between different ice thickness. Yeah. But the story is similar. We have some area over the measurement in situ location. We collect statistics, texture analysis, and again the Fisher score plus our expert opinion on what parameters to use in the model. The challenges for the model. First and foremost, the dataset size. It seems that 20 to 50,000 samples is enough. It can be enough. It probably depends on your application and the data you have. But in our case, the dataset variation inside each ice class was relatively big, and the correlations, or actually even the Fisher scores, showed us already that the relationships between different parameters and the ice types are not very strong. Then maybe even the most biggest concern was that we didn't have any in situ measurements of ice types, so lack of any validation data. Even though the experts, I will trust the expert, and everybody should trust the experts in Keskkonnaagentuur in terms of what information they provide. But nobody has been on the ice and measured the type of ice and say that this one is a strong ice and this is fast ice or whatever. Moreover, the method they classify the ice is a bit different compared to the one that we are able to at the moment develop on the satellite product. And basically, well, finally, the selection of neural network itself is a challenge since nobody really knows what will work. So the solution came by experimentation and looking what is the maximum test accuracy or minimum training loss, and this is the method for this model at the moment. Here is an example. We could basically alter the numbers here. We could play with dropout layer and also activation function. Also how deep the network itself is, but otherwise all the information we had on the performance was the training or testing accuracy and loss values. And final method is given here on the flowchart. This first pre-processing part was done on XML graph on ESTHub. Here you see the first outcomes were the visualizations on the web service. From here on, all of this part is made in Python 3.7. Models were implemented with Keras, and the method or as the software is built in a way that basically select want to train. Yes, if you want to train, then you load the annotations and go and over this route, if not in operational way at the moment, as it is on ESTHub, it goes from here. So the first results for extra wide images visualizations. Here you probably don't see very well all the ice sites are marked. Then the first water and ice classification, and the ice areas are divided into 3 different types as well. You see that while the train accuracy is relatively high, we still have some misclassifications. And in operational use, we had to also optimize the size of the segment that is first used in classification, because otherwise, if we had very small areas, the image would be very mixed. A lot of water areas between ice, and this was not the result that Keskkonnaagentuur wanted. And also the prediction confidences as well, which is quite relative information in many cases. For example, all the water areas are relatively high. Blue is number 1. So the model is quite confident in predicting water, but in prediction of ice, it is still quite hesitant. Same story for interferometric images. Here the accuracy, overall accuracy during the training was similar, but in operational use it has shown poorer results. And currently I'm not really sure how to fix this. I have some ideas, but this is for a future. For lakes, since Peipsi and other larger lakes didn't have any prior ice information, all of this had to be made manually. And here we actually got, during the training, even better results. You see here, ice and water is very well separated. The train accuracy is over 90%. But the thickness model, even though it shows some results, these results I wouldn't trust, since the data amount inside the model is very small, and there isn't any strong relations between the ice thickness and the SAR signal at the moment. Maybe after a few years, when all the voluntary people report ice thickness in different areas during different times or over the different winters, then we might have large enough data set to produce meaningful outcomes. Other operational workflows during the project was, I guess the most valuable one was the coherence values from Sentinel-1 interferometric wideswath. These areas correspond very well to fast ice, for example, very stable ice. So this is very useful information. And one Copernicus Marine Service product as well, which shows ice drift and the speed of the drift. Then optical, Sentinel-2, Sentinel-3, we made 2 different composites. This one is presented in website as well. And then cloud mask and snow mask from Metabix algorithm. Yeah, so overall, the project was valuable learning process. I have many new ideas how to improve the product or the ice classification. It might have some better future. In terms of ESTHub, the process is based on data. So as new data is downloaded, the process begins. We were one of the first projects to fully use this option on ESTHub. And the ice products are available about 5 hours after the overflight. Here I must say that if somebody is really depending on fast information from satellite, then Python is not the way to go. Python enables a lot of different good things, but in operational applications, it lacks speed. I was asked not to talk long about the challenges that we faced during the operational workflow setups. But for me, at the starting of the project, the system was relatively unknown. There wasn't much information or training. I wouldn't say there was lack of support, but the support maybe was busy with other activities. So we didn't receive information maybe sometimes even 2 weeks. And we had to modify our timeline quite many times. And also restrictions on the process or the software on the ESTHub are also things to consider. But otherwise, I would say that it is still one of the best local satellite data processing platform. And that at the current state, myself, if I have some new ideas, ESTHub is the first place to go for me to do any large scale data processing. And so it should be for you as well. And that's it for me today. Thank you.
Okay, thank you for an excellent presentation. But do we have some questions to Sander? Maybe I can ask myself, what are your plans to finally to get to distinction of this nine classes, not this intermediate? Also, I understand that it was also a big effort to get to this intermediate classification, but are there some plans to go to the end to this classification into 9 classes?
This is a good question. Well, the problem, I must show you the one figure here. The problem is how the ice is classified. Here you see that, for example, this number 3, it's let's say it's strong ice, but it actually is 7 to 8 over 10 areas is ice. Rest is water. So I'm not entirely sure at the moment how to make this knowledge teachable. But we'll see. One possibility would be using convolutional neural networks, which I actually tested as well in the beginning. But these are much more resource-intensive models, and maybe some scientific projects would solve this. But in operational application, the simple the software is, the better.
Yes, I totally agree. The simple, the more reliable. And about the thickness, yes, indeed, the thickness has been for years quite practically unsolved problem. And let us see if this voluntary data gathering in someday will help to get more precise models about also about the ice thickness, which as we know has big practical value to all citizens.